Okay, in this video we're going to finish up section 5.1, antiderivatives and indefinite integration. And up till now we've been talking about general solutions. Now we'll look at initial conditions and finding particular solutions. So we've already seen that the equation y equals the antiderivative of f of x dx has many solutions, each differing from the others by their constant. This means that the graphs of any two antiderivatives of f are vertical translations of each other. For example, in the picture, we see that the graphs of several antiderivatives in this form. The antiderivative of 3x squared minus 1 is x to the third minus x plus c. And that constant is just what moves us up and down the y-axis. Each of these antiderivatives is a solution of the differential equation 3x squared minus 1. So we look, each of these light gray graphs is a general solution, x to the third minus x plus c. And there's infinitely many of them. In many applications of integration, we're given enough information to determine a particular solution. To do this, we need to only know the value of y equals f of x for one value of x. This information is called the initial condition. For example, in figure 4.2, only one of the curves passes through the point 2,4. Here's the point 2,4, only one of the curves passes through there. That's sort of how we nail down a particular solution that has this particular condition. To find the curve, we can use the following information. Here's our general solution, x to the third minus x plus c. And we know we have the initial condition. F of 2 is equal to 4. 0.24 is a solution on the curve. So if we take our general solution and put a 2 in for all the x's we see and set it equal to 4, we can solve for the constant. So f of 2 is 2 to the third is 8 minus x is 2 plus our constant c is equal to 4. And if we solve that for c, we get the value c is negative 2. So we go back to our general solution, and in place of this plus c, we plug in the c that we found, negative 2. That is our particular solution. So here in example 7, it says find the general solution of this, and then find the particular solution that satisfies this initial condition. F of 1 is equal to 0. So first let's find the general solution. F of x is going to equal the antiderivative of 1 over x squared dx. And let's rewrite that with a negative exponent. The antiderivative of x to the negative 2 dx. And when we perform the integration, we raise the power by 1 up to a negative 1 and divide by the new exponent negative 1, which just means we put a negative out front and we add our constant c. And to get rid of our negative exponent, that is going to be negative 1 over x to the first plus c. And of course we're going to stick with our given condition that x has to be greater than 0. This is our general solution. And then we are given an initial condition. We know that 1, 0 is somewhere on one of the curves in this general solution, in that family of antiderivatives. So we have our initial condition, f of 1 is equal to 0. So if we take our general solution and we plug in a 1 for the x, and we set the whole thing equal to 0, we can solve for c. So we're going to have negative 1 over, again our x we're replacing with a 1, plus c is equal to 0. So negative 1 divided by 1 is negative 1, and then we add that to both sides. We're going to get c is equal to positive 1. So this sort of nails down the curve and gives us our particular solution, f of x. It's the same thing as our general solution, negative 1 over x, but now we know it's not just some arbitrary constant. To satisfy our initial condition, we need a constant of 1, negative 1 over x plus 1, with x being greater than 0. This is our particular solution. It looks like down here we have a graph. Let's look what this looks like graphically. So in the light gray are all the functions in the family of antiderivatives. -1 over x plus c with different constant values. But we were given an initial condition. We knew that 1, 0 went through one of the curves. So that sort of nailed it down. We only had this curve to deal with. We found our particular solution of -1 over x plus 1. That's the curve that went through our initial condition point. Solving vertical motion problems. We did these before, dealing with position, velocity, and acceleration. We had our position function. We derived that to get the velocity function, and then we derived that again to get acceleration. Now we're just going to go in reverse. So, a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. First, find the position function given the height, giving the height s as a function of time t. So let's see, we know a couple things here. We know s of 0. Our initial height is 80. Our initial height is 80 feet. We know that our first derivative, s prime of 0, is our initial velocity, and that's 64 feet. And if we think back, our second derivative of these equations was always our gravitational constant. The second derivative of t is -32 feet per second. Feet per second squared, excuse me. So there's our gravitational constant. Now we're sort of going to go backwards. We know our second derivative, s double prime of t, is equal to -32. So let's take, we can use this to find our first derivative. S prime of t is going to be the antiderivative of -32 dt. Integrate with respect to t. So when we do that, we're going to get -32 t plus the constant c. Now we can solve, we'll call that c sub 1, we can solve for that constant by using our initial velocity. So using our initial velocity, we know that s prime of 0 is equal to 64. So that's a point on the curve, 0, 64. Let's replace t in our equation we found here with 0 and set it equal to 64. So we're going to have -32 times 0 plus c sub 1 equals 64. And this is nice and easy. -32 times 0 is 0. So we get c sub 1 is 64. So c sub 1 is 64. Now, if we want to find the position function, s of t, we're going to take the antiderivative of what we found previously. That's the antiderivative of s prime of t with respect to t. So we are looking for the antiderivative of, here our equation was -32t plus c sub 1. Well, we found c sub 1, so it's -32t plus 64. Now we're going to find the antiderivative of that with respect to t. Get rid of some of this here. And I guess we can get rid of that too. So, when we work on the antiderivative here, we're going to have -32t squared divided by the new exponent of t, or 2, plus, this is going to be 64, t to the first power. Plus, we get another constant. Let's call this one c sub 2. And -32 divided by 2 is -16t squared plus 64t plus our arbitrary constant. So now we're going to use our initial height. We knew the initial height, s sub 0, was 80, so 0, 80 is a point on that graph. So again, if we go through this function we just found and plug in 0 for x's, or t's in this equation, it's t's. 64 times 0 plus our constant c sub 2. We know our initial height was 80, so this is all equal to 80. And again, this works out real nice. 0 squared is 0 times negative 16 is 0. 64 times 0 is 0. So we know right away c sub 2 is 80. So there's our equation. Let me erase a little up here, get a little more room. So, s of t, our position function, is we found negative 16t squared right here, plus 64 times t right here, and we solved for c2. We found our constant was 80, plus 80. So there's our position function giving height s as a function of time t. Now, Part B says, when does the ball hit the ground? So if we think about this, when we did these problems before, it's a negative something squared. It's a downward opening parabola. So we have our initial height. We throw the ball up. It comes down. Our x-axis is the time it takes. So how do we find out when the ball hits the ground? We set our position function equal to 0. And here, if we factor out, we can factor out a negative 16. So we're going to be left with t squared minus, what's that going to be, 4t minus 5 equal to 0. And right here, if we want, we can divide by negative 16, and that 0 divided by negative 16 is still 0. And now we have a quadratic that we can factor. And that's going to turn out to be t plus 1 and t minus 5. And now we set each term independently equal to 0. We're going to get the ball hit the ground at either time is negative 1, a second before we threw it, which doesn't make sense. Or when we set the second one equal to 0, we get t equals 5. 5 seconds after we throw the ball up in the air, it's going to hit the ground. Again, let's take a peek at this graph here. So here's our graph. We're at initial height of 80 at time 0. We throw the ball up with some initial velocity. It goes up, hits its peak, starts to come back down, and then it hits the ground. The x-axis is the seconds that this took to occur. At time 0, we were just throwing the ball. 1, 2, 3, 4, 5 seconds later, we've come down and hit the t-axis, where that tells us that the ball has hit the ground. So before you begin the exercises for the homework, be sure you realize that one of the most important steps to integration is rewriting that integrand in a form that fits the basic integration rules. To illustrate this point farther, here are some additional examples. Our integral is 2 over the square root of x. Well, we can pull the 2 out, and we can rewrite the square root of x as x to the negative 1/2. We integrate by raising the exponent by 1 and dividing by the new exponent and simplifying. Here we have a quantity squared. Foil it out. Once we have it foiled out, we can just integrate each term independently. Here is another example where we have a single term denominator with a multi-term numerator. Break it up into pieces. X to the third over x squared is x to the first. 3 over x squared becomes 3x to the negative 2. And then we can integrate each piece. In this one, we have x to the 1/3 times the quantity x minus 4. Distribute. Here we would add the exponents. X to the third times x to the first is x to the 4/3. And then we would have 4 times x to the 1/3. And then we have it again in independent pieces that we can simply integrate by raising the power by 1, divide by the new exponent.